Recording in progress.
Alrighty. So I was just saying, this is a schematic here of the neutron star density profile. The inner core of the neutron star is extremely dense, several times the density of an atomic nucleus. And that's in fact so dense that we can't reproduce those conditions in laboratory experiments, nor can we calculate the structure of matter there directly from first principles without making significant approximations. And so for these reasons, the structure and composition of the matter in the inner core of the neutron star is still an unsolved puzzle. The way that we can try and probe the properties of this matter is by looking at neutron star observables like masses and radii, because the structure of the neutron star is a function of the properties, the microphysical properties of the matter that makes it up. In particular, neutron star structure is determined by the balance of gravity that wants to collapse the star and the pressure gradients that arise from the nuclear interactions, from microphysics inside the star. The equation that governs this is the TOV equation, which is just the relativistic generalization of the hydrostatic equilibrium equation for stellar structure, and basically balancing the pressure gradients here on the left with the gravitational attraction on the right. The other ingredient that goes into this equation that determines the structure of the star is this thing called the equation of state, which is the relationship between the internal pressure and the matter density. And so this equation of state, in terms of the stellar structure, is what encodes all the details of the interactions between hadrons that produce an effective pressure in the star that holds it up against gravity. And so if we want to learn about the fundamental properties of neutron star matter, we want to determine what this pressure density relation is, what this equation of state is. All right, so on the next slide here, on the left, I'm plotting different theoretical calculations of this equation of state for neutron star matter. So pressure as a function of density shown here on a log scale plot. And as you can see, there are many different models here, which each correspond to a different calculation of nuclear theory. And if you look at their pressure at a few times the nuclear saturation density, the density of an atomic nucleus, what you see is that different nuclear theory predictions can differ by as much as an order of magnitude in what the pressure inside a neutron star will be. And moreover, each of these estimates for the equation of state are done within some particular framework that involves approximate treatments of the interactions between the neutrons. And in general, they don't come with error estimates. So each one is sort of a best guess at the equation of state, but as you can see, the predictions don't necessarily agree. So this is the situation just coming from nuclear theory without any input from observations. But because of this TOV equation that relates the equation of state to neutron star observables, masses and radii, we can constrain the equation of state by constraining neutron star masses and radii. So every prediction for the equation of state shown here on the left is in one-to-one correspondence with a mass radius relation here on the right. And so by measuring neutron star radii at a particular value of the mass, we can begin to rule out individual models from nuclear theory. And that in turn tells us something about the ingredients that went into the calculation of these nuclear theory models. So how do we actually go about observing neutron star matter? So of course, I will get to gravitational waves, which is one of the methods that I think has yielded the most insight into neutron star matter in the last few years. Although I did say we can't reproduce neutron star matter conditions in the lab, we can get kind of close. So there are terrestrial experiments that can constrain the parameters of nuclear matter, so matter made up of neutrons and protons. These are things like studies of heavy nuclei, nuclear resonances, heavy ion collisions, that sort of thing. You can constrain the properties of nuclear matter and then extrapolate to the conditions that exist inside neutron stars. Usually this means extrapolating the higher density to zero temperature, and then also usually doing an extrapolation in proton fraction. And so these aren't sort of direct experiments on neutron star matter itself, but they can be informative at lower densities, and that provides some constraints just through correlations with higher density behavior. But one of the most informative ways to learn about neutron star matter on the astro side is by looking at pulsars. And so in terms of electromagnetic astronomy, we have accurate mass measurements for a number of heavy pulsars. The heaviest one weighs in at about 2.1 times the mass of the sun. And what that does is it sets a lower bound on the maximum mass that a neutron star can support. And that in turn tells you something about the high density behavior of the equation of state, because it's basically got to have enough pressure gradient to support stars that heavy. One sort of challenge for using these pulsar masses is that the pulsar surveys are subject to selection effects that aren't necessarily well understood. And in addition to survey selection, there's also the unknown binary evolution processes that produce some systems that have EM bright neutron stars, so pulsars, versus others that do not. And so in particular, the maximum mass that we observe in the pulsar population need not be exactly equal to the maximum mass the equation of state can support. It's possible that formation channels limit the maximum mass in the population. In terms of X-ray astronomy, in the last few years, there have been very precise neutron star radius measurements through X-ray pulse profile modeling by the NICER observatory, which is an X-ray observatory mounted on the space station. The way this works is that neutron stars, some of them have hot spots on their surface, thought to be from where accreted material had landed on the star and heated up a small portion of the surface. As the pulsars rotate, we observe a modulation in the pulse profile in X-rays from these hotspots. And because the neutron stars are so compact that there are relativistic corrections to propagation effects, basically the space-time is curved and the light is propagating through that curved space-time, you can use those propagation effects to read off basically from the space-time metric what the neutron star compactness is, and then given a mass measurement, you can figure out what the radius is. So for instance here, when the neutron star's hotspot is on the far side of the neutron star, you can get some kind of like lensing type effect where you can see the hotspot for longer than you would if it were a less compact star. And that informs basically about the compactness and hence the radius of the star. So those are two electromagnetic probes of neutron star matter that have been very informative in the last few years. The best place to probe neutron star matter, though, is neutron star mergers. When you have, in particular, two neutron stars in a binary neutron system inspiraling, so orbiting their common center of mass, emitting gravitational waves, eventually merging, and potentially producing electromagnetic emission also when they merge, which can be observed. So in terms of specific matter signatures from these neutron star mergers that inform our understanding of dense matter, during the inspiral stage when the neutron stars are still well separated, tidal forces deform the neutron stars, and those deformations end up leaving an imprint on the phase evolution of the gravitational waveform, which we can measure. And that tells us, in turn, about the density profile in the neutron star. So unlike the electromagnetic emission from neutron stars, which comes basically from the surface or the magnetosphere of the pulsars, the gravitational waves are directly sensitive to the mass distribution inside the stars and carry information about the density profile, and hence directly get at the structure. When the two neutron stars merge, there may be an electromagnetic counterpart signal, possibly a gamma ray burst or a kilonova, which is the afterglow of all the material that is ejected as these two neutron stars merge. And the kilonova properties, like the light curve, can also be informative about neutron star matter. One example is based on the electromagnetic emission after the first observed binary neutron star merger, GW17817. We were able to bound the lifetime of the remnant from this merger, which collapsed to a black hole. And that lifetime translates to an upper bound on the maximum mass of a neutron star. Namely, these two neutron stars merged, they produced some remnant. It didn't collapse immediately to a black hole, but it collapsed reasonably quickly to a black hole. And that suggests that the remnant mass was very close to the maximum mass for a rotationally supported neutron star, which then you can map backwards to the maximum mass for a non-rotating neutron star. And then finally, I'll mention the neutron star mergers, even after the merger occurs in the post-merger phase, are rich in information about dense matter. If we are able to observe the gravitational waves from the oscillations of the remnant as it's sort of settling down after the merger, those tell us about the dynamical properties of neutron star matter at finite temperature, whereas the in-spiral observations tell us about cold neutron star matter. And it's the remnant that is going to probe the absolute highest densities that can be achieved in neutron stars. So we haven't detected post-merger gravitational waves yet, but with future detector upgrades, it's quite likely that we will at some point. All right.
Phil,
yes, question.
But can I challenge you a bit on the statement that gravity waves are going to provide a more precise test of EOS than, say, X-ray measurements? I mean, if you can get a precise distance to a neutron star by using Gaia, in a host globular cluster distance is well determined, then, and you have a well-defined thermal component to the spectrum, is it really clear that's less precise than what LIGO will be able to achieve with, on the tidal deformability, for example?
Mm-hmm. Yeah, so I think the main thing there is it may be the case that an individual radius measurement may be precise than an individual tidal measurement from gravitational waves, but I think over time, gravitational wave detector sensitivity is such that we will be detecting, many tens of these binary neutron star mergers, and I think combining the information from all of them together is likely to win out over the X-ray measurements. Another thing is that I think one sort of systematic source of uncertainty in the X-ray measurements, at least this hotspot-based thing, the pulse profile modeling, is that it's sensitive to the geometry of the hotspot, the configuration of the hotspots, which has to be determined simultaneously along with the radius. And it's not, there's no first principles theory for the shape that these hotspots have to take, right? So that gets determined along with everything else. And if you pick a different hotspot model, you can get a slightly different radius. Does that answer the question?
Thanks. Yeah.
Okay. So just to illustrate the different signatures of neutron star matter coming from these mergers, I want to show a simulation of a binary neutron star merger from the SXS collaboration. I'll hit play on this video and talk through it here. So we're seeing two neutron stars in blue there in the middle, getting closer and closer together. During the in-spiral phase, you can see the waveform evolving at the bottom. The frequency of the gravitational waves is going to sweep up as they approach merger. You can see now that there's some tidal deformation and then disruption, so material being blown off, which will create an electromagnetic counterpart. And then you see the remnant oscillating, ringing down basically, as we're now in the post-merger stage of the gravitational waves. And so the in-spiral part tells us about tidal deformations. The post-merger part tells us about the oscillation frequencies of the remnant. Both inform us about neutron star matter, and then the electromagnetic counterpart, given some understanding of how the ejected matter is going to produce electromagnetic radiation in different parts of the spectrum, that will also inform about neutron star matter. I'll just let this play through one more time. In yellow, that's showing the gravitational radiation coming off the binary. And yeah, purple is the ejected matter. All right. So I'm going to focus in this talk on the observation of in-spiral gravitational waves, because that's sort of the cleanest measure we've had so far from gravitational waves of the equation of state, and it's what I focus on in my work. And so let's just talk through in a little bit more detail how the matter information actually gets imprinted on the gravitational waves. So during the in-spiral, the non-uniform gravitational field from one neutron star will deform the other star, causing it to become oblate, basically giving it a quadrupole moment. And because gravitational waves are sourced by time-varying quadrupoles at lowest order, basically, in addition to the orbital quadrupole moment from having two masses orbiting their common center of mass, the tides set up two smaller quadrupole moments on each of the neutron stars, which are just going to add to the total quadrupole moment of the system. That means that there's a little bit more power in gravitational radiation that's going to be emitted, and so that's going to draw energy out of the orbit a little bit faster, with the net effect that a system of two neutron stars with tides like this is going to arrive at merger a little bit sooner than the equivalent system for point particles. And so this shows up as a phase shift in the gravitational waveform, which is shown down here in the plot at the bottom, comparing the point particle case, which is basically the binary black hole case here in green, to two binary neutron star systems, one with a soft equation of state, meaning small pressure gradients, more compact star, versus a stiff equation of state, which has a larger radius for a given mass, larger pressure gradients. And basically, the stiffer the equation of state, the bigger this mismatch in phase at merger compared to the BBH case. And so when we observe gravitational waves, we can try and measure this phase offset versus the case for point particles. We just model the waveform with and without tidal effects and see this difference. So, right, and so the amount of phase shift is quantified in terms of this parameter called the tidal deformability lambda. This is just a dimensionless quantity that measures the size of the induced quadrupole moment on the neutron star, this Qij, in units of the applied quadrupole tidal field, this Eij. And there's a factor of m to the fifth just to make lambda dimensionless here. The reason it's the binary black hole case that is the relevant comparison is that black holes turn out to have zero tidal deformability, whether spinning or non-spinning. And so in terms of tidal deformability specifically, they behave as point particles. This idea that black holes should have zero tidal deformability is an interesting topic in its own right. There's been debate in the literature, but fundamentally black holes are vacuum solutions, and tidal deformability is expressing something about how gravity is moving fluid elements, moving matter around in the star. And so it sort of makes intuitive sense that black holes should have zero tidal deformability, but this has been shown in various works cited down here. So the upshot for tidal deformability is that it depends on the internal structure of the star. Essentially, a stiffer equation of state that has more support against gravity is going to produce a fluffier neutron star that's easier to deform and hence have a larger tidal deformability, versus a soft equation of state, which will have a smaller tidal deformability because its star is more compact and difficult to deform. So stiff equations of state have larger lambda at a given mass than soft ones. And then all else being equal, if you take a heavier neutron star, that's also going to have a smaller tidal deformability simply because it's going to be more compact.
Can I just ask a quick question? When you say a hard equation of state, I seem to have got a loop here going. It's not uniformly hard or soft. That is to say, there's an exterior that everybody would agree on.
Yeah.
And then And so the question is, so this is all, usually the soft and hard is associated with supernuclear densities. Oh, I see. Okay, so it's tacked on to a lower density EOS.
That's right. Yeah. So those are all good points. So firstly, when I say stiff versus soft, those are relative terms. And I'm also speaking in a loose kind of average sense, because the equation of state, so strictly speaking, like the stiffness or softness would be like the slope in this plane. But the slope doesn't have to be constant. It can change at some point or another. And so equations of state can be soft at low densities and stiff at high densities, or vice versa. So I'm just saying, loosely speaking, if the equation of state on average is stiffer, then lambda is going to be stiffer, larger, all else being equal. But you're absolutely right. At low densities, where we essentially know the equation of state through nuclear experiments, first principles calculations, we know it more or less up to, say, the nuclear saturation density. Chiral effective field theory, which is a first principles calculation, can get it maybe as high as twice nuclear saturation density, but beyond that, it's really uncertain. And so when I talk about the neutron star equation of state, I really mean it at super nuclear densities.
And another related question: are thermal corrections important in the merger? That is to say, what kind of entropies are we dealing with?
Yeah, that's another good question. So before merger, thermal corrections are not important. The temperatures inside the neutron star are well below the Fermi temperature. But at merger, and certainly for the post-merger phase, then yes, thermal corrections are crucial. And the equation of state, is effectively different, because you have to deal with the finite temperatures.
And is that known, the form of that correction?
I would say that it's more uncertain than the zero temperature equation of state. So there are models just like this. There are individual models like this that will fold in the temperature dependence. But it's even more uncertain than the zero temperature case.
Okay, thank you.
Mm-hmm. No problem. Okay, so right. So I was just saying tidal deformabilities here. Basically, a measurement of lambda is a proxy for a measurement in the equation of state, because there's this one-to-one mapping between the equation of state and this lambda versus m relation, just like the mass radius relation I showed before. All right, so that was a little bit on how we actually learn about neutron star matter from gravitational waves. What are the neutron star observations we've made with gravitational waves to date? So what are we working with here? Here is a big schematic of everything that LIGO, Virgo, and Kagra have seen so far. Black holes are in blue, neutron stars are in orange. Electromagnetically observed black holes and neutron stars are also shown here. But what I'm focusing on, the observations that are of particular interest to me, are these orange dots down at the bottom. Those are the neutron stars that we've seen in gravitational waves. There are 2 binary neutron star mergers observed to date. There are 2 confident neutron star black hole mergers observed to date. And then there's 1 or 2 other sort of marginal neutron star black hole events that might be real, might just be instrumental noise. And then there's even a further 1 or 2 events that are sort of on the threshold, where we're unsure whether their lighter components are neutron stars or very light black holes. So I'm going to quickly breeze through a couple of these observations, because this is what informs our dense matter knowledge to date. So of course, there's the first binary neutron star merger observation, GW 17817, that saw 2 neutron stars of sort of canonical mass, about 1.4 solar masses, merge and form a black hole. This was observed with an electromagnetic counterpart. It confirmed that BNS mergers are a site for short GRBs. The kilonova observations confirmed that our process elements can be made in binary neutron star mergers. And of particular relevance for this talk, there was a measurement of this tidal deformability lambda for the 2 neutron stars. Basically, the initial discovery placed an upper bound on tidal deformability, but a subsequent reanalysis that modeled the correlations we expect between lambda for the two components, led to tighter bound and tidal deformabilities. This is just because we believe that there is one universal equation of state for all neutron stars, and therefore lambda 1 and lambda 2 have to be related in a particular way that depends on whatever that equation of state is. They're not uncorrelated. And the constraint that you end up with when you take these correlations into account is shown, well, the green shading here is the posterior, the 90% credible region is shown with the green solid line here. And the takeaway is basically, here you have different black equation of state models that are making predictions for lambda 1 and lambda 2 for the observed masses in this system. Some of the stiffer ones are ruled out, and the softer ones tend to be preferred down here at the bottom. There was a subsequent binary neutron star merger that was observed during LIGO's third observing run in 2019. This one involved a heavier neutron star, around 2 solar masses, and one with a sort of more conventional mass. This system was interesting because its total mass is heavier than any other known neutron star system. Particular compared to the galactic binary neutron stars that we observed, its mass is a definite outlier. In part because of these larger masses, however, no tidal effects were observed and no electromagnetic counterpart was identified. That's also a product of the signal to noise ratio for this event being smaller. It was further away. And masses being heavier mean that even though we expect there to be tidal effects, they're too small to observe. That's borne out in this plot here, which is comparing the actual measurement of tides for this second binary neutron star event in blue to where we expect the tidal deformability to be in orange. And what you can see is that the measurement uncertainty is much larger than where we expect the tidal deformability to be. So this event is not very informative when it comes to dense matter. Meaning that our gravitational wave information to date comes primarily from GW 170817, with the other events basically setting a kind of upper bound just from a null result. So what can you do to turn these tidal deformability measurements into actual information about dense matter? The simplest thing you can do is do Bayesian model selection on the different equation of state models that come from nuclear theory. So this was done in one LIGO-Virgo collaboration paper that I participated in, just taking a bunch of those models that I showed on the previous slide and computing the Bayesian evidence in favor of them. Do they explain the observed tidal deformabilities? And what you find is the same story that came out of the previous plot, where the softer equation of state that produce a more compact neutron star, all else being equal, are favored over the stiffer equations of state. Now, you might want to try and do better than that for a number of reasons. Firstly, although the nuclear theory predictions are good, the real equation of state probably isn't going to be exactly one of them. And in particular, none of the nuclear theory predictions come with error bars, so it's kind of difficult to compare across models sort of thing, or to go outside of the individual models that are given to us from nuclear theory. So an alternative way to constrain the equation of state is instead to parameterize a phenomenological model for the equation of state and then try and infer what the parameters are. So basically to cut out the nuclear theory predictions and just try and directly map the astrophysical observations into the equation of state space. The simplest way you can imagine doing this is turning your equation of state, pressure versus density, into something that's like a piecewise linear function in this log-log plane, and then inferring what the slopes are, basically, if you fix the joints. So this is something called a piecewise polytrope model, and you can do the inference in a Bayesian framework where essentially you can think of it as working in a big Monte Carlo algorithm. You draw some values for the slopes for these parameters gamma, then you build your equation of state, and that sets a prior distribution over the masses and tidal deformabilities because they're related by the equation of state. And then for your choice of parameters, you say, what is the likelihood that this equation of state explains the data that's been observed. You marginalize or average over the uncertainties in the measured masses and tidal deformabilities, and then you iterate in your equation of state samples, and in this way you build up a posterior distribution over these gamma parameters, which gives you a distribution then over the equation of state once you reconstruct it. That's one way to do things. You can do a more sophisticated parameterization where instead you expand, you take a spectral basis of functions basically, and you expand that way, and you can more closely match the shape of the nuclear theory equations of state. But basically all these parametric schemes are doing the same sort of thing. They're breaking down the equation of state into a basis of functions and then inferring the coefficients of that basis of functions. And so doing this for GW170817's tidal deformability constraints, what you end up finding is that the equation of state relative to the prior distribution, not informed by the observation, is softer than predicted at a few times nuclear saturation density, but has to be relatively stiff at high densities in order to support the observed 2 solar mass pulsars. So that's treated as another observation alongside the gravitational waves in this inference. Additionally, you find for the central densities of the neutron stars that were involved that they're between 2 and 4 times nuclear saturation density. What does this mean for the neutron star radius, which is a sort of equivalent way of thinking about these constraints? Well, it tells you that the radius is smaller than you might have thought. So the initial range nuclear theory models could predict is maybe between 9 or 10 kilometers and as much as 16, even 17 kilometers. GW170817 sets an upper bound on the radius of about 13 kilometers or so, just favoring the most extreme models, basically.
We have a question.
Okay, yes, question.
Yeah, on these equation of state constraints,
Mm-hmm.
do they take into account rotation?
Aha, so that's a good question. For GW170817 specifically, the analysis was done in 2 ways. One, which assumed the neutron stars were slowly spinning, and those are the results I'm showing here. And one that allowed the neutron stars to have spin at the level of the measurement of the tides and the masses. But basically, when we're talking about these tidal deformabilities, those are the tidal deformabilities for a non-rotating neutron star. The picture of tides is complicated by rotation, but this sort of lowest order quadrupole tidal parameter is going to be there regardless of spin. And so in short, we don't think that there was rapid rotation to the level that it would change the picture of our equation of state constraints here, but there is a set of measurements done on masses and tidal deformability that allows for that possibility. Does that answer the question?
Yep, thank you.
Okay, so right, so parameterizing the equation of state and inferring the parameters is one way to proceed for equation of state inference. I want to briefly touch on a different way of doing things, motivated specifically by the fact that parameterizations don't necessarily capture all the degrees of freedom that are available to the equation of state. In particular, some nuclear theory models predict that there's a sharp phase transition between a hadronic phase and, say, a deconfined quark phase at high densities. This looks like a jump in the density at fixed pressure in the equation of state. And what I'm showing here in the green box thing is that parametric schemes are bad at capturing sharp features in the equation of state like this. So basically the nuclear theory equation of state data is the purple dots, and then there's 2 parametric fits to that in black and red that don't really capture that kind of behavior. And so you might want to try and get away from a direct parameterization and do something different to not artificially restrict the kinds of functional form that the equation of state can take. This is something that I worked on, that I developed with another postdoc, Reed Essick, from the University of Chicago at the time. He's now at the Perimeter Institute, where instead of parameterizing the equation of state directly, we use Gaussian processes to try and emulate the different shapes the equation of state can take. So we use Gaussian process regression or Gaussian process-based emulation to build a model for possible equations of state that doesn't depend directly on parameters. So instead of parameterizing the function itself, we build a covariance matrix between the sound speeds, so just the derivatives of the equation of state at different pressures, where we say that the covariance between the sound speed at two different pressures is Gaussian, okay? And the hyperparameters that describe that Gaussian are going to be tuned to reproduce specific equations of state from nuclear theory that we use as a kind of training set, okay? You can build in causality and thermodynamic stability, and in practice, you can basically tune many of these Gaussian processes to different theoretical equations of state and then build an overarching process over all of them. But what this does for you is it gives you essentially a process that can produce a random or synthetic equation of state that loosely resembles what you've trained it on, but isn't exactly what you've trained it on. So it both interpolates and extrapolates from existing equations of state. This is shown schematically in this plot here, where red are the equation state we train on. Everything in black and blue is what comes out of the Gaussian process model, so it occupies a much larger volume in the prior space than what we train on, but then some fraction of these equations of state would be thrown out by the fact that we've observed two solar mass neutron stars, so their maximum mass has to be above that. Anyways, the point here is just to say that there are alternatives to parameterization, but the way you actually do the equation of state inference is the same. Instead of sampling in parameters, you just sample in realizations from the Gaussian process. If you use this non-parametric or Gaussian process-based model for the equation of state, do the same kind of equation of state inference as I showed before, but now fold in not just the gravitational wave observations, but also those X-ray observations, so like the nicer radius measurements for the two pulsars that's measured so far, and the masses from the heavy pulsars. You can end up, in total with fairly good constraints on the equation of state. So what's being shown here, pressure is a function of density. These are 90% credible contours going from the prior. So this is just the equations of state in black that come directly out of the Gaussian process model, not constrained by any observational data. Once you require them to explain the masses of the heaviest pulsars, you get the light blue constraints. So basically this stiffens the equation of state at high densities. And then when you fold in the gravitational wave tidal measurement, that softens the equation of state at those intermediate densities. That gives you the green contour. And then finally, the nicer radius measurements give you a lower bound on the pressure at those intermediate densities, so that you end up with this reasonably tight constraint in blue. Also of interest here, we can infer what the central pressure and density for the heaviest known neutron star is. And it comes out with a central density of about four times nuclear saturation density, with support up to about 6. Same picture you can make for the mass radius relation, and what these constraints boil down to are that the neutron star radius is between about 11 and 13 kilometers, and it seems to be remarkably consistent across the whole neutron star mass spectrum. In particular, the most recent nicer measurement of a radius is for this J0740 pulsar, which is the heaviest known one. And the radius measured there is consistent within uncertainties with the radius that we measure at 1.4 solar masses. This is maybe an indication that the maximum mass is heavier than 2.1 solar masses, because normally the equation of state models like to have a smaller radius as they approach the maximum mass. Basically, the mass radius relation turns over at the maximum mass. But what we can say for sure is that there doesn't seem to be a large difference in the radius of the heaviest neutron stars compared to those with more typical masses. All right, so in my remaining time here, I just want to touch on some applications of this equation of state knowledge. So, can we use it to answer some questions in astrophysics, nuclear theory, that sort of thing? Firstly, what do our gravitational wave observations tell us about exotic matter that may be in neutron stars? So there's been proposals that there could be a population of quark stars. So these are stars made up entirely of deconfined quarks. That possibility, I think, is severely challenged by current observations. Namely, it predicts an equation of states that's softer than we observe. There's also problems with pulsar glitches and R mode instabilities. But the possibility that there could be a quark core, so deconfined quark matter existing in the middle of the neutron stars, that is very much alive, and it's consistent with current observations, although not required. You can explain all observations with purely hadronic matter. But there are a bunch of models in the literature that either have completely distinct hadronic and quark phases or even mixed phases between them. And yeah, our observations to date tell us that you can't rule out either scenario. One interesting specific constraint that you can get from the astrophysical observations to date has to do with the sound speed in neutron star matter. So that's what's shown here on the right, sound speed squared as a function of density. There's this conjecture from perturbative QCD calculations that neutron star matter at the very highest densities should asymptote to a sound speed squared of 1/3. So this is the prediction for non-interacting ultra-relativistic massive particles that we expect to be true in like the really asymptotically high density limit well beyond neutron stars. But in the absence of strong interactions between hadrons or some other phase, we might expect the sound speed to monotonically asymptote this limit. What I'm showing here in blue is the constraint on the sound speed inside the star after all the observations have been considered. And while it doesn't exclude sound speed curves that always stay below this dashed conformal limit, the bulk of the models, the bulk of the curves that would exist in this blue contour would certainly have a violation of this conformal limit. And what this would suggest is that there is a phase of matter that is strongly interacting and non-conformal, for instance, something called quarkionic matter, as opposed to just plain old hadronic matter. So it's the case that neutron star observations to date suggest that this conformal bound is violated, although it need not be the case. The probability is that it is, and this would indicate the presence of some unusual phase of matter that's not just pure hadrons. Another kind of investigation you can do is say, is there a strong phase transition in the equation of state where there's this jump in pressure?
Could I just get that,
Sure.
that point clarified? So for a range of equations of state that you showed that people play around with, I think you're inferring that they routinely violate that C squared max equals 1/3.
Yeah, that's correct. It's not just for the handful of equations of state that people use, but it's if you take either a parametric or a non-parametric model that's built out of those to resemble them, but kind of explore a broader range of the prior space for equations of state. The bulk of them, after you condition on observations, do violate that limit. Yeah.
Well, wait a minute. Now, let me be clear. So
Yeah.
there are the specific functional forms that people have, and then there is your attempt to fit it by these Gaussian processes. And were you saying that the bound is a result of the parameterization?
No,
or
so
a result of the equations of state themselves?
Yeah, so let me back up. So here I'm showing the results for my Gaussian process equations of state, but those that come out of the Gaussian process without being conditioned on any observations are inside this black envelope. So they're below this solid black line. And the majority of those do live under this conformal limit, okay? So there's definitely support for things in the prior that violate the conformal limit, but there's more support for things that live below the conformal limit. When you condition on the observations, then that flips. Now there's more support for things that violate the conformal limit, although there are still some models that are below it.
Where does APR set on this?
APR I'm pretty sure is constructed so that it doesn't violate the conformal limit, but I would have to look at that in detail. Basically, the models that violate this limit are the ones that build in on purpose strong interactions or some unusual non-hadronic phase.
So if you have hybrid quark hadronic matter, which seems on my reading to be the most likely case, rather than a pure quark matter phase, then would that violate this limit?
I believe so, but I would have to check. So
I think the APR work does allow for the existence of that phase at the center, where their purely hadronic fits are restricted to lie outside that central core. But
yeah, I mean, the thing that I know is that models that are, there are models that are specifically designed to break this, and there are models that have, specific strongly interacting phases, and they break this. In terms of historical models, I would have to check them individually, but my guess is most of them probably stay below the limit. Yeah. All right, so we're getting close to the top of the hour. Let me just make a couple other points. You can check systematically in the equations of state that you're constraining in this way, the same way we constrain them for the sound speed. You can see whether these models have phase transitions in them or not. So these strong phase transitions that can produce a separate hybrid star branch in the mass radius relation, which is disconnected from the hadronic stars if the jump in the equation of state is large enough. You find that there's basically no strong evidence in favor one way or the other. So both are compatible with current observations. But you can see that there's different characteristics to the equations of state, whether they have this strong phase transition like in green or they do not. I won't mention constraints on nuclear physics, but you can map the astrophysical quantities back to nuclear parameters, or indeed quantities that you measure in the lab, like the neutron skin thickness. Let's see. So one interesting thing you can do with equation of state information is use that to classify gravitational wave events you observe in future. So for instance, after those two binary neutron star observations, LIGO and Virgo observed GW 190814, which was an unusual merger because its secondary component was 2.6 times the mass of the sun, putting it above known neutron stars in mass, but below known black holes, raising the question, is it a neutron star that's especially heavy, or is it a black hole that's especially light? And one thing that you can do is just systematically compare its mass to an estimate of the maximum mass from the equation of state, which is shown here in red, and compute the probability that this thing is consistent with a neutron star, namely that its mass is below the maximum mass. If you do that, you find that for one particular estimate of the non-rotating maximum mass, it's only got a 5% chance of being below that, meaning that it's likely to be a black hole. And even if you consider spin, which I'm not showing here, and you allow the neutron star to exceed this MTOV, TOV non-rotating mass limit, and be rotationally supported, even in that case, it's very unlikely to be a neutron star. So the secondary in this system is probably the lightest black hole ever observed. Equation of state information also can go into electromagnetic counterpart predictions. So there were two neutron star black hole mergers discovered last year. We did not see an electromagnetic counterpart associated with these because we think the neutron stars got swallowed up whole pretty much by the black holes. And that's borne out by predictions for the amount of ejected matter, which is what's shown in this plot on the color scale here, as a function of the spins involved and the mass ratio involved. Another input here is the equation of state. And basically, instead of fixing some equation of state model from the literature, which may or may not be favored, you can actually just average over a posterior distribution of, on the equation of state and fold in those uncertainties in a self-consistent way.
Could I just ask a question on this? So have the numerical calculations been done? Presumably they have for these cases. I'm interested in the question of this swallowed whole concept. Do they actually see that the neutron star can be swallowed whole, or does it develop some kind of tidal tail going in or something like that?
Yeah, so for these particular neutron star black hole coalescences, the mass ratio especially was such that we do not think that there was any significant tidal disruption or indeed any measurable tidal deformation. So basically, no matter was ejected in these mergers. If you look, the amount of, just from this plot here, the amount of ejecta is less than 2% of a solar mass for most of the parameter space. And this is a calculation for an NSPH that's similar to the ones that were observed. So if the mass ratios were a little bit more equal, so if the mass ratios were a little bit more equal, there'd be more ejecta. If these things were observed closer to us, if they had happened closer to us, then there also would have been more of a chance to see the electromagnetic counterpart if there was any ejecta. But we really just don't think in this case that there was much ejecta at all. Yeah. Okay, so so another thing just I wanted to mention here, you can compare the maximum mass that you observe in the gravitational wave population to the one you infer from the equation of state.
Can you hear me?
Yeah. Yeah, is there another question?
No, just you have a couple more minutes.
Okay, so let me wrap up with this point then. Today, the LIGO-Virgo collaboration put out a population analysis of the neutron stars and all the black holes it's seen to date. And one of the things you can do from that, infer the neutron star mass distribution that's observed, look at the maximum mass that comes from that and say, is it the same as the maximum mass we infer from the equation of state? They need not be the same because it's possible that the heaviest neutron stars just don't end up in merging compact binaries due to the astrophysical formation processes and astrophysical evolution processes. But if you compare the orange curve here for the maximum mass from the equation of state to the blue ones we infer from the population, they're consistent within errors for now. And that's about as much as we can say with only 6 neutron stars confidently observed in the gravitational wave so far. But in future, with order 50 observations, we'll be able to get a much more precise measurement of the maximum mass in the population. So I will stop there. I'll take any questions if there are any questions in the last minute or two here.
Perfect. Thank you. Thank Philip for a nice talk. Anybody from the audience, just free to unmute yourself. Maybe write your question in the chat. So if nobody else is going.
Well, maybe I could get you to project into the future, let's say 5 years downstream. How will all these things likely improve?
Right, great question. So next year, LIGO is going to turn on again, we hope anyways, next year, with improved sensitivity. And during the next observing run, I think I maybe have this written here, we can expect maybe 4 binary neutron stars with signal and noise ratio greater than 20. So 20 for signal and noise ratio is like a loose threshold on when we expect there to be measurable tidal information. And so in the next observing run, maybe we'll get 4 more. And if any of them are, even half as informative as GW170817, then adding those into all the other observations will actually improve our equation of state knowledge significantly. The next observing run is going to be at what's called A+ sensitivity, which is beyond design sensitivity. Then we should expect order 10 binary neutron stars with LIGO and Virgo. But the real game changer will be Cosmic Explorer, which hopefully will be built in the 2030s, along with Einstein telescope in Europe. And then we'll get, order hundreds of binary neutron stars with incredibly loud signal and noise ratios. And, then the goal will be really mapping out the entire mass radius relation or mass tidal deformability relation and answering, precise questions about composition and things like that.
A question from here.
So I think you talked a lot about how the pre-merger gravitational wave signal constrains the equation of state.
Mm-hmm.
How does the post-merger gravitational wave signal constrain it? Because
Right.
you Yeah. There's a lot of oscillations within the neutron star, which
Right.
are detectable.
That's right. Yeah. So the post-merger phase is more complicated. You have in the frequency spectrum for the post-merger a dominant peak that you expect from just the quadrupole oscillation of the remnant. That occurs in the kilohertz frequency range, a few kilohertz. It's dependent on the hot equation of state of the remnant, okay? So that's going to be correlated with the cold equation of state, but there's going to be temperature corrections that come in. And so if you can predict, for every finite temperature equation of state, what the peak post-merger frequency is going to be when you observe it, then you can use that to constrain these equation of state models, in the post-merger regime. But basically, you're dealing with, an additional degree of freedom versus the pre-merger stuff. And so it's almost a separate problem. It's more complicated. If you know the cold equation of state, that will help us learn more about the finite temperature equation of state. But the game is really about measuring these post-merger frequencies. And the other thing is you need simulations of neutron star mergers to make any progress there. So in the in-spiral case, you can do semi-analytic calculations of the tidal deformabilities. So you don't need to simulate everything. But in the post-merger regime, you really do need simulations to make the predictions.
Correct. If we do not have any more questions, let's thank Philip again.
Thanks for listening, everybody.
Thank you for everything. So feel free to remain here if you want to discuss with Philip.